Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 7 of module 3, wherein we are discussing the electric and magnetic properties of atoms and molecules. Now friends, on the basis of whatever discussions we had earlier based on the electrical and magnetic properties of the atoms and molecules, now hereafter we will see the spin only formula and the orbital contribution of them to magnetic moment. So basically look at how this idea generates. Now we all know that the origin of magnetism in an atom, it lies in the motion of negatively charged electrons. This is what we have seen in our first slide of the magnetic motion. Okay. Now, the overall magnetic moment of an atom is the resultant of the magnetic moment which is generated by the spinning motion of the electron, and it is called as the spin magnetic moment. Usually we represent this spin magnetic moment by mu s. Okay, and usually we represent the orbital motion of the electrons, uh, which is called as orbital magnetic moment, which usually we represent as mu L. So subscript L we usually refer for this particular orbital motion of electrons. Now, when a molecule containing unpaired electron is placed in magnetic field, the electrons, they try to get aligned in the direction of magnetic field, isn't it? So this all we all know. Now this can be achieved in two ways. So what are these two ways? How it can align themselves into the direction of magnetic field? Either by adapting the spin motion in the direction of magnetic field, or by adapting the orbital motion in the direction of magnetic field. So in order for an electron to contribute to the orbital angular momentum, the orbital in which it resides must be able to transform into an exactly identical and degenerate orbital, say by a simple rotation, and it is particularly the rotation of the electrons which induces the orbital contribution, isn't it? So let us take an example of the octahedral and tetrahedral complexes. So in case of octahedral complex, what we usually have the T2G and EG sets. So in an octahedral complex, the degenerate T2G set of orbital, say for example dyz, dzx and dxy is shown over here. Okay, so these three orbitals of T2G set is shown over here. So they can be interconverted in between themselves by say 90 degrees rotation. This is quite possible. You can see from these figures. So they can be interconverted with each other by 90 degrees rotation. However, say the orbital in EG status, or orbital which are in EG kind of subsets, that is d2z square or dx square minus y square, you can see over here, and you can see their geometry also. From this you can see here, from these figures you can see that they cannot be interconverted by rotation about any axis. Why it is so? Because the orbital shapes are different from each other, and therefore they cannot be interconverted, and therefore an electron in the EG set does not contribute to the orbital angular momentum, isn't it? And it is said that it is quenched in this fashion if for EG particular subset. Now in the free ion case, the electrons can be transformed between any of the orbitals. Why? Because they are all degenerate, but there will be still a partial orbital quenching, Why? Because the orbitals are not identical, and therefore the electrons in the T2G set, they do not always contribute to the orbital moment. You can take the example of say T2G3. So in such case, what will happen? An electron in the dxz orbital cannot by rotation be placed in the dyz orbital, as the orbital is already it has an electron on the same spin. So this process is also called as quenching. Now in case of compounds of 3D block elements, the orbital motion is quenched, or what we can say, it is prevented. As a result, one can take into account only the spin motion, neglecting the orbital motion. Now in such cases, the spin only magnetic moment will be given by this particular expression, square root of 4s into s plus 1 into Bm, where this Bm is the Bohr's magneton. Okay, and in this particular expression, uh, the each basically the each unpaired electron has a spin quantum number half. So for n electrons, what we have, s is equal to n by 2. So if I substitute this value n by 2 over here, s is equal to n by 2, I get this particular expression, and which gives me mu s is equal to square root of n into n plus 2 into Bm. Okay, so this is what I could get from the from this particular description. Now similarly, there are however certain cases that the spin only formula does not give the correct values of magnetic moments. Now such cases, they arise in octahedral complexes where T2G orbitals are unsymmetrically filled, and in case of tetrahedral complexes where T2 set is unsymmetrically filled. And see over here. Okay, what do I mean is, say for example, if you see the cases of octahedral and tetrahedral cases over here, you can understand the thing. Now in case of compounds of which the elements of say higher D series, wherein second and third transition series kind of compounds you consider, and or say especially you take the compounds in lanthanides. So the orbital motion is not quenched in such cases, and therefore it is necessary to consider the orbital contribution to magnetic moment for lanthanides or even actinides. Now in higher transition series elements and in lanthanides and actinides, the spin motion and orbital motion couples together to give the new quantum number J, which is given as J is equal to L minus S when the shell is less than half filled, and J is equal to L plus S when the shell is half filled or more than half filled, isn't it? So my value of J will be related to the magnetic moment in this particular fashion. So mu effective is equal to mu J is equal to G into square root of J into J plus 1 into Bm, where this G is the Landé's splitting factor, and it is given by this particular expression. So it is actually nothing but the ratio of spin magnetic moment to spin angular momentum. So it is basically where you can see the formula over here. So the values obtained using this formula, they are very close to that of observed values of for the lanthanides. So this can be summarized from, I mean, using this formula, the observed and the calculated values, they match with each other. So now it is also worthwhile to mention here that due to the quenching of orbital motion of metal orbitals, which has got say with ligand orbitals in complexes of 3D series, so the elements which has got 3D orbitals, the magnetic moment of dipositive ions, it increases with the number of electrons up to say manganese 2 plus, isn't it? and then it decreases due to pairing of electrons. And therefore, you can see from this particular figure the magnetic moment as a function of number of d electrons in a parabolic curve. Okay, so you can see the maxima at this d5 orbital of manganese 2 plus, isn't it? Now in case of tripositive ions of lanthanides, it is expected that the gadolinium should have the highest value of magnetic moment as it has 7 unpaired electrons. But the case is not so simple in lanthanides. Why? Because due to the orbital contribution to magnetic moments, it does not respond as you are expecting. This is so because 4f orbital is 2 shell deeper, and so the orbital motion is not quenched by the ligand orbitals. So the variation in magnetic moment, it can be seen in this particular figure. You can see the first maxima at say around 59, and then it goes again at up to 67. So the value is particularly maximum for holmium and dysprosium instead of gadolinium, isn't it? So this is something which is very apparent from these particular figures over here, isn't it? We can calculate the magnetic moments based on the formula that we have seen here. So let us calculate the magnetic moment of manganese 2 plus ions. So it is a d5 system, and therefore all the 5 electrons are unpaired. So as manganese belongs to 3d series, the orbital motion is quenched, and therefore the spin formula will be like this. Now uh, uh, it should be used for the magnetic moment. Now we have got all 5 electrons unpaired, and therefore the resultant spin will be given by this formula. So it will be 5 by 2. So if I use this formula, I can substitute this value and I get the answer 5.91 bm Bohr magneton. So now it can be calculated by using this formula as well. I can substitute n is equal to 5. So again the same results can be obtained. Similarly, calculate the second numerical is calculate the magnetic moment of cobalt 2 plus ion. Now cobalt 2 system we know. So as cobalt belongs to 3d series, the orbital motion is quenched, and hence spin formula will be mu s is equal to square root of 4s into s plus 1 into bm, and therefore it should be used for the magnetic moment. The number of unpaired electrons are 3. Okay, so if I calculate the resultant spin momentum, I can calculate using this, or I can simply calculate using this formula mu s is equal to square root of n into n plus 2 into bm. Now taking n is equal to 3, I reach to same answer. So the magnetic moment of cobalt 2 plus ion is 3.87 bm. Let us see a very interesting discussion over here based on the magnetic properties of complexes of particularly 3d series elements. This will give you very fundamental idea about the utility of this particular concept. Now we all know that the crystal field theory, it could successfully explain the properties of complexes formed by various transition metal ions. Now in case of 3d series elements, the orbital contribution to the magnetic moment is negligible, and the magnetic moment is given by simple spin only formula. Okay, so this is what we have seen, spin only contribution. However, the complexes having unpaired electrons, they are paramagnetic, and while those with the electrons in paired form are diamagnetic. So the magnetic properties which are based on this kind of complexes, I mean wherein you can have all the possibilities of pairing up and unpaired electrons. So based on their unpaired electron and paired electrons, we can discuss in detail the magnetic properties of octahedral complexes and how they are behaving based on it. So based on it, there are 2-3 kind of possibilities. Now there can be several types of octahedral complexes. So first we will classify the octahedral complexes with say D1, D2 and D3 configurations. What do I mean by this? These are the complexes. They will have the configuration of T2G1, T2G2 and T2G3 respectively. And all of these electrons, they are basically unpaired, and so they are paramagnetic in nature with the increasing magnetic moments. So if they have got 3 electrons, so you can see D1, I mean T2G1 is 1, T2G2 and T2G3. Okay. Now let us understand this aspect in little more detail, because this will give us the important understanding of the concept. Now, how high spin and low spin octahedral complexes are formed? In some complexes, there is a possibility of more than one type of electronic configuration. And the configuration in which the number of unpaired electrons are less has low value of spin, and therefore it is called as low spin complex. I'll repeat. The configuration in which the number of unpaired electrons are less has low value of total spin, and thus they are called as low spin complexes. That means it depends on number of unpaired electrons. On the contrary, if the number of unpaired electrons are more, it is said to be a high spin complex. Therefore, the spin state of complex, it depends upon the relative values of crystal field splitting energy, which is denoted by this delta O value, and pairing value, or which we call it as a pairing energy. So these are the two important parameters one needs to take care of. That means the spin state of complex, it will depend upon the relative value of what is the value of crystal field splitting energy and what is the value of pairing energy. So what is pairing energy? Pairing energy is the energy which is required for two electrons to pair up in the same orbital, like here. So the pairing energy is required to pair up the electron in the same orbital. Now the relative strength of these two energies, that is crystal field splitting energy and the pairing energy. So the relative strength of these two energy, it will depend upon the nature of ligands. So based on it, there are two cases which are possible. So what are these two cases? Number one is the case if my ligands are weak. So in such case, due to weak field ligand, the crystal field splitting is less than the pairing energy. Okay. And therefore, the electron will definitely go to higher energy level and remains unpaired. So a high spin complex will be formed. Look at this figure. This is the case. On the other hand, if my ligands are strong, now in such cases, the strong field ligands, they cause large splitting of d orbitals. You can see this part of the figure. They cause large splitting of d orbitals, as a result of which my crystal field splitting energy will be greater than the pairing energy, and therefore the pairing will be preferred and low spin complex will be formed. So in octahedral complexes with say D1, D2 and D3 configurations, if d orbital contains 1, 2 or 3 electrons, they will definitely go to T2G orbitals and remain unpaired, and therefore they will always have a high spin complex. They will always prefer high spin complexes, and the electronic configurations, it can be shown like you can see over here. We can even see the further details of this. This table particularly will give you number of unpaired electron. You can find out the magnetic moment. Now substitute this value over here. N is equal to 1. If you substitute over here, 1 plus 2 is 3. So 3 into 1 is 3. The square root of 3 bm. So square root of 3 bm is 1.73 bm. I can find out from the value of magnetic moment what kind of spin it has and what kind of 3D complex it is, octahedral complex it is. Likewise, if you substitute the value of 2, so 2 plus 2 is 4 into 2, 8, square root of 8. Likewise, I can substitute this value. In all such cases, the magnetism is paramagnetic, and the examples are given over here. These are the examples. Now, the second part of octahedral complexes, which has say D4, D5, D6 and D7 kind of configurations. Now, these complexes, they can be either high spin or low spin because number of electrons are greater now. So both the possibilities are always there. So the high spin complexes have higher value of magnetic moments while low spin complexes have lower values. This we have already seen. So the low spin complexes of D6 configurations are diamagnetic in nature due to all paired electrons. You can see over here. So number of unpaired electrons, therefore, in high spin complexes. However, in case of low spin complexes, if you see, there are no unpaired electrons, so it is diamagnetic in nature due to all paired electron. Now this is the case of low spin complex, whereas in case of high spin complex, it has got all the D4, D5, D6, D7. You have got unpaired electron, and therefore it will form the high spin complexes, isn't it? So when the ligand is weak, so the extent of splitting is also less, and delta O is smaller, and therefore crystal field splitting energy is less than the pairing energy. Now in all such cases, high spin complexes is formed, and when the ligand is strong, the extent of splitting is more, that is crystal field splitting energy is greater than the pairing energy, and therefore in such case low spin complex is formed, and which will give us the idea about, I mean, the figure which we have seen in the previous case, in the previous slide. This will give you the clear idea. So same is followed over here. You can see number of d electrons, 4, 5, 6 and 7. For high spin complexes, the arrangement is like T2G3 and EG1. In case of D5, T2G3 and EG2. In case of D6, T2G4 and EG2. And in case of D7, T2G5 and EG2. So number of electrons, if you try to see that way, 4, 5 or 4, 3. So accordingly, magnetic moment can be calculated over here, because since the magnetism is paramagnetic, the complexes will be high spin complex. Now in certain cases you can have the low spin complex as well, because in D4 system this is also possible to have T2G4 kind of arrangement, or T2G5 kind of arrangement in D5, or T2G6 kind of arrangement in D6, and T2G6 EG1 kind of arrangement in D7. In all among all these cases, T2G6 case is the only case where the low spin complex can have the diamagnetic kind of nature. The examples are given over here, what kind of examples you can have. So low spin arrangement and high spin arrangements, I have tried to show over here, and the complexes are also mentioned in front of their electronic configurations. Now in these particularly 4 cases, the relative values of crystal field splitting energy and pairing energy will decide basically what kind of complex it will form, whether it will be high spin complex or low spin complex. Similarly, I mean, what we have seen now, D4, in case of D4, D5, D6, D7, these are the kind of arrangements again we have shown over here. Now, one must note here that the high spin state, it does not involve the additional pairing energy, because these electrons are already paired in free metal ion, and low spin states, they take into consideration only those pairing which are additional. Okay, so this is just additionally to note down. Now third part is, there are certain cases wherein we have the octahedral complexes with D8, D9 and D10 kind of configurations. So now in case of octahedral complexes with D8, D9 and D10 configurations, only one type of distribution of electrons is possible. You can see from this table. It is very exemplary. With the increase of numbers of electrons or d electrons, the number of unpaired electrons, it decreases. You can see the electronic configuration, and therefore the magnetic moment also decreases from D8 to D10. You can see magnetic moment also decreases from D8 to D10. And the magnetic properties of tetrahedral complexes, if you see before that you can see over here, as I said, that magnetic moment of these octahedral complexes, it decreases from this to this. You can see the magnetism which is involved. Now in case of D10 system, you can see all the levels, T2G and EG levels, they are paired up, and therefore it has to be diamagnetic, isn't it? Whereas in these two cases, it can be nickel 2 plus or copper 2 plus kind of thing. Complexes, it will be paramagnetic in nature. So the electronic configurations are shown over here, the possible electronic configuration, but there is nothing much possibility of forming the different kind of complexes, and therefore the only possible configurations are represented over here. It is also interesting at the same time to note the behavior of or the magnetic properties of tetrahedral complexes as well, because basically metal ions in tetrahedral fields, in tetrahedral complexes, it may be treated by the same procedure as discussed during the octahedral complexes. However, for tetrahedral complexes, it is found that, say for D1, D2, D7, D8 and D9 configurations, only one spin state is possible. And for D3, D4, D5 and D6 configuration, both the high spin as well as low spin states are possible. So the existence of low spin states requires the splitting energy greater than the pairing energy. So my crystal field splitting energy in case of octahedral complexes is only about 45% in tetrahedral complexes as compared to the octahedral complexes, that is we see crystal field splitting, that is delta O. So what is the crux? Crystal field splitting in case of tetrahedral complexes is only about 45% in tetrahedral complexes, which is as compared to the octahedral complexes crystal field splitting. As a result, the pairing energy is higher than the crystal field splitting energy, isn't it? So my pairing energy is higher than the crystal field splitting energy, and therefore the tetrahedral complexes are generally high spin. They contain same number of unpaired electrons as that of the isolated metal ions, and therefore the magnetic moment is almost the same as that of the metal ion. So this is what is about the tetrahedral complexes. Now this concept of magnetic properties is very crucial and very important in understanding the formation of octahedral and tetrahedral complexes, which was explained in crystal field theory as well. So this concept was very much related uh, herein, and therefore after the discussion of magnetic moments and magnetic properties of atoms and molecules, we have taken this particular part of inorganic chemistry into the discussion, which enabled us in having the importance of the magnetic moment in determining the category of complexes in case of octahedral and tetrahedral, in case of particularly in case of 3D series of elements. Let us see one last numerical here. Now magnetic moment of this particular complex is 1.73 Bohr magneton. Now we need to draw the d orbital splitting diagram for this particular complex and show the location of electrons in it. Now what is given actually? It is given that my dipole magnetic moment is 1.73 Bohr's magneton, and therefore the number of electrons must be 1. because since it is 1.73, that is, you know the formula, mu s is equal to square root of s n into n plus 1. So if n into n plus 1 value is 1.73 bm, that means n must be 1, and therefore the number of unpaired electron must be 1 here. So it is now clear that we have got one unpaired electron. That is clear. Now the complex is of Fe3 plus, and Fe3 plus is d5 system. It is very clear from this particular complex formula, and therefore we have got d5 system. So, and we have got only one unpaired electron. So what can be the electronic configuration? Therefore the two configurations are possible after splitting of orbitals here. That is, one is T2G3 Eg2 with all 5 unpaired electrons. In such case, all the 5 electrons will be unpaired. And the second possibility is T2G5 Eg0 with only one unpaired electron. But since we, from the magnetic moment value, we know that this particular is value corresponding to only one unpaired electron. So from the value of this mu, the second configuration, that is T2G5 and Eg0, is correct, and therefore the figure should be as shown over here. So this is how we can utilize the concept. So friends, this is particularly end of this particular lecture, and in this lecture we are finishing with the complete course paper of physical chemistry paper 4, wherein we have started with right from the conductometric understanding, conductivity understanding. Then we have seen in module 2 electrochemical understanding, electrochemistry we have seen, including Nernst equation and its application. And in module 3 we have seen the electrical and magnetic properties of atoms and molecules. So thank you friends for your cooperation.